Hello everyone, welcome to lesson 13 of our Golang course. In this lesson, we will continue our exploration of bitwise operators in Go and dive into the world of bitwise shift operators. So let's get started. Bitwise shift operators are a powerful tool for manipulating binary representations of an integer value. They allow us to remove and append bits. In Go, we have two shift operators, the right shift operator denoted by a double right arrow and the left shift operator denoted by a double left arrow. Both these operators are binary, meaning that they work with two operands. In the upcoming slides, we will explore more examples for both of these operators to illustrate their use. Similar to bitwise logical operators, these shift operators are essential for low-level bit manipulation. One example is creating a bit mask that is actually created with a shift operator. Again, we will look at the examples and see how that is done. A bit mask enables us to extract or set a specific bit in the binary representation of the integer value, efficiently assessing individual flags or bits stored in a binary representation. Let's look at the right shift operator. The right shift operator in Go is used to remove bits from the number. When performing the operation A right shift I, it removes I bits from the number A. Consider this example here. We have the number 15 represented by binary 1111 and we are shifting it towards the right by 2 bits. This operation will give you 0011, which means we have effectively removed the 2 bits from the end. The result of this operation is 11 as the 2 rightmost bits are removed from the original number. So after right shifting by 2 positions, the result is binary 11. Right shifting I bits from a number will result in a number that is equal to A divided by 2 raised to power I. When you perform the operation A right shift I, you are shifting bits of number towards right by I position. Each shift to the right effectively divides the number by 2. So shifting I bits to the right is equivalent to dividing the number by 2 raised to power I. Here we have another example of right shift operation. We have the decimal number 20. The binary representation of 20 is 10100. Then we are shifting the number by 2 bits, which will effectively remove the last 2 bits of this number and result in 101, which is decimal 5. So you can see it is equal to 20 being divided by 2 raised to power 2, that is 4, which leads us to 5. The left shift operator in Go appends 0 bits to the number. When performing operation A left shift I, it appends I 0 bits to the number A. Again, let's perform the operation on 15. Here we have 1111 and we are shifting this number left by 2 bits, which will result in 111100. So you can see 2 zeros have been appended to the number. Left shifting I bits of a number A will result in a number that is equal to A multiplied by 2 raised to power I. When you perform operation A left shift I, you are shifting bits of number towards left by I position. Each shift towards the left effectively multiplies the number by 2. So shifting I bits to the left is equal to multiplying by 2 raised to power I. Let's now look at an example of left shift operation. Now we have the opposite, that is 5, or binary representation 101. We are left shifting it by 2, so the result is 10100, which is equal to decimal 20, which is also equal to 5 being multiplied by 2 raised to power 2, that is 4. Let us look at some more interesting bit manipulation operations that can be performed by combining bitwise shift operators with bitwise logical operators that we saw in the previous lesson. First up, we have one left shift I, which will result in a single bit being set in the ith position while the rest of the bits of the number are 0. The expression 1 left shift I is a common technique used to set a specific bit at position I in number 1 while keeping all other bits as 0. This is what we use to create a bit mask with only one bit set to 1 at the ith position and rest of the bits set to 0. Operation A or 1 left shift I will result in ith bit of A being set to 1. When you perform this operation, this particular part, you are creating a bit mask with a single bit set to 1 in the ith position and then performing a bitwise OR with the original number A. This effectively sets the ith bit of A to 1 while leaving other bits unchanged. The operation A and not 1 left shift I will set the ith bit of A to 0, also known as the bit clear operation. When you perform the operation A and not 1 left shift I, you are again creating a bit mask with a single bit set to 1 in the ith position and then performing a bitwise AND NOT operation with the original number A. This effectively sets the ith bit of A to 0 while leaving the other bits unchanged. Next, we have the operation A not 1 left shift I, which will invert the ith bit of A. When you perform operation A not 1 left shift I, you are creating a bit mask with a single bit set to 1 at the ith position and then performing a bitwise OR operation with the original number A. This effectively toggles the value of ith bit in A, flipping it from 0 to 1 or from 1 to 0 while leaving the other bits unchanged. So these are few examples of how shift operators are used in conjunction with the logical bitwise operators to perform bit manipulation at a lower level. Let's look at some examples of bitwise shift operators and how they are used for bit manipulation. In the first example, I is 3 and the expression 1 left shift 3 will result in a binary representation of 1 0 0 0. As you can see, the bit at position 3 is set to 1 and all other bits are 0. In the second example, A is 5 or binary representation 1 0 1. I is 1 and the expression A or 1 left shift 1 will result in binary representation 1 1 1 1, where the bit at position 1 is set to 1 while the other bits remain the same. In the third example, A is 7 or binary representation 1 1 1 and I is 1. The expression A and not 1 left shift 1 will result in a binary representation 1 0 1. Where bit at position 1 is set to 0 while the other bits remain the same. In the fourth example, A is 5, 1 0 1. The expression 5 not 1 left shift 0 will result in binary representation 1 0 0, where bit at position 0 is inverted from 1 to 0 while the other bits remain the same. So essentially what we are doing here is in the first example, we are creating a bit mask. The only bit that is set is at position 3. Next, we are performing a set operation where we are using a bit mask first, a bit mask where only the bit at position 1 is set. We are using this to make sure that bit at position 1 in the number is set. Next, we use the bit clear operation again with a bit mask to make sure that whatever we have at bit position 1 is set to 0 or is cleared. In the end, we use the NOT operation with a bit mask and inverted the bit at position 0. So this is how bit manipulation is done with the shift operator and logical bitwise operators. As we talked about this in the bitwise logical operators lesson, exercise caution when utilizing bitwise shift operations with sign integers. Even though the sign is preserved, it is always recommended to use any bitwise operator with unsigned end. Also know, shifting bits to right or left can result in potential overflow of value or loss of essential data. Since when you shift right, you are removing bits or resulting in loss of data, or when you are shifting left, you are appending bits, which could overflow the size of the data type. So by being mindful of the data type and the shift type, you can prevent unexpected consequences and ensure the integrity of your operations. That's it for the lesson. In the next lesson, we will explore bitwise shift operator with code. Thanks for watching this video. If you have any questions, please post a comment under the video or reach out to our Discord server. I will see you in the next lesson. Happy coding.